what is a beam column? Beam columns are members that are subjected to both axial compression and bending, while bending is as important as axial compression. For example, in an axial construction, columns and frames are typical beam columns. The difference between eccentrically loaded column and a beam columns are: in eccentrically loaded column, axial pressure is a primary effect while bending is a secondary. Whereas in beam column, axial pressure is a primary effect while bending is also important. First is about beam column with concentrated lateral load. Consider a simply supported member of length L which is simultaneously acted on by a transverse load Q and axial force P. The assumptions made here are the material behaves according to Hooke's law, deformations remain small, and that the member is laterally braced so that it can only bend in vertical plane. The external moment at a distance x from the origin is m is equal to qx by 2 plus py, and the internal moment is minus ei y double dash. Equating both, we will get ei d square y by dx square plus py equal to minus qx by 2. Dividing the whole equation throughout by ei, we will get d square y by dx square plus k square y equal to minus qx by 2bi, where k square is p by ei. General solution of the equation is y equal to a sin kx plus b cos kx minus qx by 2p, where a and b are the arbitrary constants. Applying the boundary conditions, at x equal to 0, y will be 0, and thus b we will get as 0. And another boundary condition is that at x equal to L by 2, dy by dx equal to 0. Equating, we will get a equal to q by 2 kp into 1 by cos kl by 2. Now substitution of these results in the general solution, we obtain the final equation y equal to q by 2 pk into sin kx by cos kl by 2 into kx. Instead of considering the deformation of the entire member, now we will limit our attention to the midspan deflection, that is del. So let x equal to L by 2, we will obtain del will be q by 2 pk into sin kl by 2 and cos kl by 2 into kl by 2, where q by 2 pk will be tan u minus u, where u equal to kl by 2. Now multiplying and dividing the whole equation by lq by 24 ei, we will get del will be q lq by 40 di into 3 tan u minus u whole divided by uq. Here the left hand factor in this relation is a deflection that would exist if the transverse load Q were acting by itself. So we introduce another notation del naught equal to Q LQ by 40 di, and thus we rewrite the equation as del will be del naught into 3 tan u minus u whole by uq. Now making use of the power series expansion of tan u, that is tan u is equal to u plus uq by 3 plus 2 by 15 u5 u raised to 5 plus etc. Now substitution of the series of tan u in the equation will get like this, and here u square will be p by ei into L square by 4 into pi square by pi square, which is equal to 2.46 p by p square. This we will get by equating the equations 3.2 and 3.6. Okay. Finally, we will obtain the result as del equal to del naught into 1 the whole by 1 minus p by pc. Now, the maximum bending moment in the member is max equal to qi by 4 plus p into del. And substituting the del value here, we will get the final equation as max equal to ql by 4 into 0.18 p by pcr the whole by 1 minus p by pcr. The left hand factor is the maximum moment that would exist if no axial force were present. Thus letting m naught equal to ql by 4, final equation, maximum moment in the beam column is given as max equal to m naught into 1 minus 0.18 p by pcr the whole by 1 minus p by pcr. This equation shows that the effect of axial compression on the bending moment is very similar to the effect that an axial load has on the deflection. Like the deflection, the moment that exists in the absence of axial compression is amplified by presence of an axial load. It's also interesting to note the similarity between the amplification factor for moment and corresponding for the deflection. Next is a beam column with distributed lateral load. Here also we will consider a simply supported member bent by uniformly distributed lateral load W and a set of axial forces P. Assumptions made are the material obeys Hooke's law, that deformation remains small, and that the member is restrained against lateral buckling. Here we will apply the energy method. The strain energy that is stored in the member as it bends is U equal to EI by 2 into integral 0 to 1 d square y by dx square the whole square into dx, and the potential energy equal to V equal to minus W integral 0 to 1 y by 0 integral 0 to 1 y dx minus P by 2 into integral 0 to 1 dy by dx the whole square into dx. The total energy will be U plus V. To satisfy the boundary condition, deflection y is assumed to be one of the form y is equal to del sine pi x by L. We will substitute the y value in the equation U plus V. Now, the maximum moment in the member will be Mmax equal to WL square by 8 plus P into del. We will substitute the del value here, and finally we will obtain Mmax equal to WL square by 8 into 1 plus 0.03 P by PCR whole by 1 minus P by PCR. We know that M0 will be WL square by 8, thus Mmax equal to M0 into 1 plus 0.3 P by PCR whole by 1 minus P by PCR. The maximum deflection of the beam column given by the equation 3.26 and the maximum moment is in 3.30 are thus both equal to the product of two terms. The maximum deflection or moment that will exist if only lateral load were present and an amplification factor that accounts for the effect of the axial load.